job for me to take light from the laser, which for now I will assume to be ideal, and then modulate that laser light. So, how do I modulate a laser light? I have to have some way of converting this Ps of t, which is flat in the ideal laser, that would be the green line, whose power is not fluctuating. If the power is not fluctuating, if the frequency is not changing, if the phase remains constant, then I cannot communicate anything. So, everything is constant, I am not communicating any data to the receiver. If I want to communicate, I have to change these characteristics. So, I have to change the power or equivalently intensity, or I have to change the phase and frequency. So, we will see how this can be done by postulating certain optical transmitters, okay, or optical modulators. It turns out that later, as we look at the physical implementation, it turns out that it is easier to modulate the phase of the optical signal rather than modulating the amplitude. In fact, amplitude modulation can be obtained, high speed amplitude modulation can be obtained by actually converting that into, or by using the phase modulators in a way to change the amplitude. So, we will see that one. In order to look at that, we will first start with the basic element called a phase modulator. Okay. So, we look at phase modulator, and as its name suggests, its job is to modulate the phase of the incoming light signal. So, the incoming light comes from a laser which is producing a nice optical signal having an amplitude of square root Ps or equivalently power Ps, and instead of writing this as cos omega st plus phi, I will shorten the notation and write this as e to the power j omega st plus phi, and at this point my phi or the phase does not really matter to me. So, I will remove that one from the considerations. I will simply assume that the output of this laser is a very nice optical signal having an amplitude of square root Ps and having a frequency omega s. Okay. So, this is a notation that we normally use, we do not normally use cos omega st, this is the shorter notation that we normally use. Okay. Because I can of course always recover back what that cos omega st signal is, all I have to do is take this square root Ps e power j omega st and then take the real part of it, right. So, if I take the real part of, so if I call the signal that is coming out as s of t, so if I take the real part of s of t, I get square root Ps cos omega st. This is in fact the signal that actually laser produces, but for notational simplification and mathematical manipulation, we normally go to this exponential notation. Okay. All right. So, this is the laser output. I am now going to put this one through a phase modulator. Okay. So, what should I get? Well, what I should get with the phase modulator is the phase of the optical signal. Oh sorry, I missed the phase, actually I thought the phase is unimportant, but the phase is important because I am actually looking at the phase modulator. I thought that I am looking at amplitude modulator, no, I am looking at the phase modulator. So, it is important. So, we go back and put this phase as a phi. Now, instead of having this phi to be a constant, if we somehow make the phase of the optical signal dependent upon what we are sending as the electrical signal, is that okay? So, if I take the electrical signal and then somehow alter the phase of the optical signal coming from the laser, then I have obtained optical phase modulation. So, that is all that is there to the optical phase modulator. The input is this sinusoidal signal coming out from a laser, and the output of this would not change the amplitude because this is just changing the phase. It would also not change the frequency omega s, okay, but it would change the phase to phi of t, in the sense that this phi of t will be dependent with some constants kp if you want on the signal that you are putting to the phase modulator. So, this phase modulator takes in two inputs, one is the light input in the form of the laser light, and the other is the electrical signal in the form of a voltage, and that voltage signal, let us call this as m of t. M of t could represent an analog signal, it could represent this one, or it could represent the digital realization of pulsed realization of a digital signal. Okay. So, it would represent a sequence of pulses. In both cases, this m of t is the one which will actually change the phase of the optical signal. So, this is the time domain description of the phase modulator that is sufficient for us Now, we ask what is this light going into it. I have said that light can be modeled as a sinusoidal carrier, okay, but this S of t is actually the electrical field which I am assuming is polarized in only one direction, and this signal is propagating along z axis. Okay. For now, you can think of this electric field of the laser as a oscillator output. It is just an electrical analog to the oscillator, it is an optical analog of the electrical oscillator. You can think of that way, but in the modulation literature this is typically called as the input electric field and this is called as the output electric field. Now, you might be wondering what this electric field is. Remember, light is an electromagnetic wave and you can represent this electromagnetic wave by specifying its electric field and or magnetic field. So, we have chosen to represent them with the electric field. For now, you do not, no harm is done if you simply think of this as some S of t and this one as some R of t or S hat of t, does not matter, whatever the name, whatever the symbol that you give to this one, this would just be the phase modulated version of whatever the input that is going in. Okay. Now, if you look at what is the output power will be equal to the input power. Why? Output power is Ps, the input power which is obtained by taking the electric field magnitude square, in some sort of a normalized sense, will be equal to Ps. Similarly, P out would be obtained by taking the magnitude of E out of t square, which will again give you Ps. So, this is a lossless optical phase modulator. For the case where m of t happens to be a cosine signal, but in the electrical domain, so let us say this is cos omega t plus some phi electrical signal. If this is the case and Kp is the phase modulation constant, what your phase modulator produces are 3 waves. In a approximation that Kp being very small, okay, it produces 3 waves. One is the carrier which would be fluctuating at omega s or which would be producing which would be varying at signal frequency omega s, and sidebands are omega s plus omega, this is called as the upper sideband, and omega s minus omega. Okay. The amplitude of these things will be dependent on what Kp that you are giving, but for Kp which is very small, you can think of the amplitude as being essentially unchanged at the carrier, and the amplitude of the sidebands are down to Kp and Kp. Okay. So, the amplitudes of the carrier is essentially 1 because it has not changed much, and Kp would be the amplitude of the upper sideband as well as the lower sideband. The upper sideband will also have a phase phi e, while the lower sideband will have a phase of minus phi e relation to the signal phase which is at omega s. This is the simplest case of sinusoidal phase modulation, okay. Something that we do not really look at it for now, okay, for few more modules. Okay, we have looked at the output power, input power, the electric field output and the electric field input characterization of the phase modulator. So, for our purpose, the time domain characterization of the phase modulator is it takes in some electrical input signal, puts out an electric field output which will have only its phase changed compared to the input. If you were to plot output power versus input power, it would be just equal to 1, or output power by input power ratio, that would be equal to 1 for all time t. There is no change in the power of the phase modulator. It will preserve, a lossless phase modulator will preserve whatever the input power is there and just puts it out. Now, let us look at how can we obtain amplitude modulation by utilizing cleverly the phase modulator structures. Okay. This structure is called as a Mach Zehnder interferometer, and it is based really on the idea of interferometer. What is an interferometer? Mach Zehnder interferometer. What is the idea of an interferometer? Perhaps the simplest interferometers that you are familiar with is the so called Young's interferometer, right. So, in which you had a light wave coming in from some distant source, and then you had 2 slits. So, these are the 2 slits that you had, and these slits would allow partial light to go through, and then you would put a screen somewhere far back here, and you would see that Well, at any point on the screen, the amplitude of this one would be the light that is coming from the first slit and the light that is coming from the second slit, and there is a certain phase difference because the paths of these two lights are not equal. So, any change in the path will change the phase of the light. So, depending on the phase change, you probably would have seen an interference pattern that would look like this, right. So, it would be the interference pattern that you must have seen. So, there are certain places where the interference pattern is maximum because the two waves arrive in phase, and there are certain places where they are not equal because they would arrive at different phases. So, based on this idea that you can take light, split it into two paths and delay one with respect to the other, right, and then combine them is an interferometer, and that interferometer idea is behind what is called as a Mach-Zehnder interferometer modulator, or sometimes called as Mach-Zehnder modulator MZM. So, this MZM basically works on the principle that it takes light coming from the laser. So, this would be the laser for us, and it will split into two paths, and then create or control the delay through one path, by electrical signal. So, whatever the signal that you want to transmit, this electrical signal m of t will go and control the delay through one path for the light that is propagating through it. The other path is normally not delayed and it is transmitted as it is. So, when you combine them two on the screen or an equivalent of a screen, what you get is a amplitude modulated electric field, which will then be used for amplitude modulation of the light waves. So, you start with a laser, split into two paths, control delay through one path and then combine them. This is of course not exactly how it is constructed. I mean, this is, although it is exactly how it is constructed, the actual physical details are quite different. We will talk about those physical details in the next layer where we talk about the physics behind these modulators. Okay. So, let us proceed to look at the structure itself. The structure consists of an input waveguide. These are normally made on a waveguide. So, the structure consists of an input waveguide where the incoming signal will be the electric field of the laser. So, the electric field of the laser will provide the input, and this is split into two parts by using what is called as a Y junction, which can be implemented on an optical waveguide itself. You send one through the other, and instead of what we do is, instead of delaying one with respect to the other, we kind of put two controls, okay, so that we can control the relative phase between the two. Remember, all that I am concerned is the relative delay, the relative path difference between the two arms, okay, of the interferometer, or this path difference because it converts to phase difference. I am only concerned with the relative phase difference between the two arms. To do that one, you normally use some structure. You give one input called u1 of t, the other input u2 of t, and then combine them using one more coupler or a Y junction, and what you get is the electric field output E out of t. This portion which is there here, you know, light going in and light coming out, is actually a phase modulator. Similarly, what you are obtaining here is another phase modulator, and we have already seen how to characterize the input output relationship of these two phase modulators. What we have not understood is what are these Y junctions. So, I know what if I give the input to this phase modulator which has the message signal m of t in the form of u1 of t. I also know that if I know the electric field input going into this second phase modulator whose input is u2 of t, okay, I know what the electric field outputs that I am going to get here, but what I do not know is how to deal with this Y junction which is splitting and combining light. Okay. We will again, as I said, we will talk about this split and how the physical implementation works, but for now we will simply postulate the relationship between the two. Okay. If there is no phase difference between the two arms, then whatever the power that you send must come back without any loss, assuming that there are no losses through the waveguides, there are no losses through the internal structure of the modulator, then whatever power you give, if it could be 1 milliwatt, it could be 2 milliwatt, this power would appear at the output. Okay. Accordingly, these two Y junctions have to split the power. In a typical splitter we use a 50-50 splitter, indicating that half the power goes in one arm and half the power goes in the other arm. But powers are by themselves not important here, or they are of the secondary importance. What is important is how the amplitudes get split. Okay. We will postulate that the amplitudes do get split in the form of 1 by root 2, so that when you square it the power becomes half. So, I have E in by root 2, and this power which I have will split into E in by root 2, and while we combine, we also combine them in the same fashion. You can see that depending on the structure, these splits are not exactly E in by root 2 or E in by root 2, there could be some additional phase factors that could come in, but for now we will simply assume that these splits have happened in such a way that the electric field amplitude going into the upper phase modulator is E in by root 2, the electric field amplitude going into the bottom phase modulator is E in by root 2. So, what would be the output of the first phase modulator here? Well, this would be E in by root 2. I have not shown that E in is a function of time, but it is a function of time because it is coming from the input signal, and then this part comes from this phase modulator thing, right. So, you had phi of t, and in place of phi of t you had Kp m of t. Rather than writing Kp m of t, we will use a slightly different notation here. Okay. So, I will write this as E in by root 2 e to the power j, and the frequency and everything is known. So, only thing which I have to write here would be the phase part, and that phase part I will write it as pi u1 of t divided by v pi. Let me rewrite it down here. So, for the first phase modulator, the electric field output would be E in by root 2, that is at this point which I am writing, and then you have e to the power j pi u1 of t divided by v pi. This v pi is called as the half wave voltage of the phase modulator. We will talk about what half wave voltage means when we look at the physical structure of the phase modulator. Okay. What would be the output of the second phase modulator? Well, we already know how to do that one. So, it would be E in by root 2 e to the power j pi, but this time it is not u1 of t, it is u2 of t divided by v pi. Okay. Now, how do we combine them to form the outputs? Again you take this electric field divide by 1 by root 2, this electric field divide by 1 by root 2, and then combine them. So, when you look at the electric field output E out of t, it would be the combination of this particular output, okay, which has been reduced by amplitude 1 by root 2, and this output which again has been reduced by an amplitude by 1 by root 2, and simply combine them. Okay. So, let us combine them in this way. So, what I get is E in by 2 E in of t, let me write down. E in of by 2 is a constant which can be written out, and I have e to the power j pi u1 of t by v pi plus e to the power j pi u2 of t by v pi. So, there is some difference in how the electric field at the output of the MZM is compared to the output of the phase modulator, correct. So, there is this difference between the two, and u1 of t would be the signal m of t that you would be providing, u2 of t could be the signal m of t that you are providing. Later we will see that depending on whether these two are driven with the same signs or driven with different signs, you can get different modulator outputs. Okay. But this is the relationship between input and output without simplifying further. However, we normally want to simplify to understand what is going on. We can do that by removing one of these two terms, okay, that is taking one of these two terms as common. Let me arbitrarily choose to take this particular term out to obtain electric field at the output of the MZM modulator or MZM as E in of t by 2. The phase factor which I am taking out is e to the power j pi u2 of t divided by v pi. If I take that out, what do I have left in? Well, there would be 1 in place of this e power j pi u2 of t, but here I will have e power j pi u1 of t minus u2 of t divided by v pi. Okay. So, this is what I have now. Now, this has not completely solved my problem, but what I can do is I can write u1 of t minus u2 of t as u d of t, which would represent the difference between u1 and u2 of t. Okay. So, that would represent the difference between the two signals u1 of t and u2 of t. These are electrical signals, by the way. So, please remember u1 of t's are electrical signals, u1 of t and u2 of t are electrical signals. So, further simplification can be performed by removing one half of this and then recognizing that the quantity inside is actually a cosine function, right. So, cos of x is e to the power j x plus e to the power minus j x divided by 2, sin x is e to the power j x minus e power minus j x divided by 2j. So, if you remember these two formulas from Euler's identities, that would be helpful here. So, I can think of this as this term inside this square bracket as some e to the power j x plus 1, and if I take e to the power j x by 2 as a common factor, I can write here as e power j x by 2 plus e power minus j x by 2. You can verify this by multiplying this e power j x by 2 inside. So, when you multiply, this will go and it becomes e power j x, and here it will become 1. And remember that x is nothing but pi by v pi into u d of t, right. So, by making these associations here, I can write the electric field output E out of t of the MZM modulator. Remember, we are talking about MZM modulator here. So, this would be equal to sum E in of t by 2 e to the power j pi u2 of t divided by, sorry, this is divided by v pi. So, this is divided by v pi. I have taken e to the power j pi u d of t divided by 2, sorry, again 2 v pi, and in brackets what I have is e to the power j pi u d of t by 2 plus e to the power minus j pi u d of 2, which is actually nothing but cos of pi u d of t divided by 2 v pi. So, let me just write this here probably to show it correctly. So, this would be pi u d of t by 2 v pi. So, this would be the simplified electric field of the output, okay, after taking some terms which are constant. Now, if you look at what is the relationship between input and output, sorry, this would be, there is no 2 here. So, this 2 actually should be gone, because when I take this term here, I need a 2, because cos of x is, there is a 2 in the denominator. So, I have already a 2 here at E in by 2, I will push that 2 into the brackets. So, to form that term into cos pi u d of t by 2 v pi. Okay. If you look at this expression, there are these two terms which essentially imply that there is some global phase change that is happening. Okay. There is some global phase change which is completely not important for me. Okay. So, this global phase I can ignore as long as I am looking at only one MZM, I am not connecting the output of one MZM to another MZM, I can conveniently ignore this global phase factor. Okay. For an isolated MZM that I have, which I am giving the input and looking at the output, this global phase factor I can ignore. What I am now left is E out of t, which is the electric field output, as square root P s e power j omega s t, and then I have cos pi u d of t divided by 2 v pi. Is that okay? So, this would again be a signal whose central frequency is omega s, but whose amplitude is now a function of time. So, in the frequency domain, the output would not just be a sinusoid, I mean not would be a impulse function at omega s, but it will now be modulated, because u1 of t changes with time, u2 of t changes with time, the difference between the two signals also changes with time. Have we obtained amplitude modulation? Well, not quite yet, because in an amplitude modulation, as we normally understand, the output or the signal s of t after modulation would be written something like AC cos omega s t, which would be the electrical carrier, this would be the carrier signal, multiplied by the sum u of t, where u of t is the message signal, right. This is what is called as a double side band suppressed carrier, if you remember. So, I have not yet quite obtained here. So, just to make it consistent, let me write this as u d of t being the message signal. Okay. So, this is the message signal that I have, equivalent of the message signal, but I have not yet obtained this cos omega s t is not a problem, because I can convert this into e to the power j omega s t, but then I am still left out with this cos of pi ud of t by 2 v pi. To really obtain the modulator, what we need to do is we need to understand what is the relationship between E out and ud of t in a slightly more detailed manner. We do that by drawing a graph of electric field output as a function of ud of t, okay, as a function of ud of t. We will look at it as a function of ud of t. Okay. What would that function relationship look like? Rather than looking at E out of t, let me look at this as the ratio E out of t by E in of t. This is known as the field transfer function, okay, and this transfer function or the transfer ratio, this is not exactly a transfer function in the signal system point of view, but this is the just a name for that because there is output to input ratios. Now, as ud of t changes, right. So, initially when ud of t is 0, cos of the argument 0 is 1. So, it would be equal to 1, and when will this go to 0? When ud of t is equal to v pi, correct. So, when this is equal to v pi, the cos function inside the cos function, the argument v pi cancels and you get cos pi by 2, which means it is gone to 0. So, this is at v pi. What would happen when ud of t is equal to 2 v pi? The transfer ratio becomes minus 1, right. So, this would happen at 2 v pi, this would become minus 1. So, you actually have something going to 0 and then becoming minus 1. Similarly, on this side at minus v pi and at minus 2 v pi, you get a minus 1. Of course, this will again keep repeating, okay. So, we do not really want to look at that. If you look at what is the ratio of the power which can be obtained as P out of t divided by P in of t, that power ratio will look like this. Okay. Because amplitude could be minus, but the power would be plus. Now, in the next module we will see how to make an amplitude modulator. We will also see how to make an optical pulse shaper using this MZM that we have just described. Thank you.